So, good morning everyone. So, in this lecture I am going to talk about the other set of constraints, namely the holonomic constraint problems as well as the non-holonomic constraint problems. Okay. So far we have looked at functional optimization subject to the isoperimetric constraints. So, in this lecture I am going to introduce the two other different types of constraint, namely the holonomic or the algebraic constraints and the non-holonomic constraints or the differential constraints. So, let us quickly look at let me call this constraint as the category A and this constraint as my category B. Okay. So, in the case of holonomic, as I just said, these are algebraic constraints. Algebraic constraints. I see that the constraints will be of the form g of t comma q bar equal to 0. So, these are all algebraic relations between the various components of q bar and t, where q bar in general is a vector. Right. Okay. So, I see that n is greater than equal to 2. Okay. So, when so in this case and in the let me just also briefly state what are the non-holonomic constraints. So, the non-holonomic or differential constraints are those where we have the constraints of the following form. Okay. So, these are my A and these are, let me call this relation as 1 and I call this relation as 2 for later reference. Okay. So, how to solve problems with constraints of the type 1? So, let me just briefly discuss on that role first. Okay. So, let us set up the problem in for case A. So, suppose I have a functional. So, let j be a functional, of the form, j of q bar is equal to integral from t0 to t1 of L of t comma q bar dot dt, right, and subject to my boundary conditions. Q of t0 is q0 and q of t1 is q1, right, and so these are my boundary conditions. Okay. Now, further, for consistency purposes, we must have these boundary conditions. The constraint also should satisfy the boundary condition, otherwise we will run into some trouble. So, we must have a prior assumption for consistency purpose that g at t comma q bar naught must be equal to g at t comma q bar 1, which is equal to 0 for consistency purpose, right. And also we assume we are dealing with normal problems. We assume that grad of g, which is given by del g del q1, here we are dealing with, let us say, two variable problems, comma del g del q2 is non-zero. So, here I am dealing with, let us say, in R2, right. For higher orders, then there will be more components in this expression. Okay. So, for extremals, so these conditions are for extremals, q bar in the interval t0 to t1. So, q bar in the interval t0 to t1. Okay. So then, well, intuitively it seems that this class of problems is relatively simple to solve. In fact, this is not even a new set of problems we are discussing. It seems intuitively. Why? Because notice that notice the constraint. So, if we look at this constraint, possibly we could use the constraint to solve one variable q, let us say q1 with respect to the other variable q2, and then replace this constraint problem with the corresponding unconstrained problem of one variable. So, rather than solving a constraint optimization problem with two variables q1 and q2, let us say in 2D, we could solve the unconstrained problem with respect to q1. If we could solve q1 as a function of q2 using the constraint, like we mentioned briefly in the case of finite dimensional calculus, but again we will see that we run into some problems, right. So, what I just said is the following. So, suppose again we are talking about normal problems. So, suppose for normal problems, suppose so suppose, well, I need to also number this result. Let me call this as 3, right. So, suppose for normal problems, so 3 implies that the constraint, the holonomic constraint 1 can be used to solve for one q case. The holonomic constraint can be used to solve for one q case. Then we could possibly, as I just said, we could possibly change the unconstrained problem into a constrained problem into an unconstrained optimization problem, the standard Lagrange multiplier, right. So, which means it seems intuitively it seems that an n variable constrained problem to be reduced to n minus 1 variable unconstrained problem. Right. It seems that is possible, and many times it's possible, but many times it not. So, it may or may not work, right, as we have seen several similar scenarios in finite dimensional calculus and for isoperimetric problem also. Well, not the case of isoperimetric problem, but in the case of finite dimensional calculus we saw that it may or may not work. So then what is the alternative out of it? So, the alternative, to look at the alternative, let us consider the following. Suppose I look at a perturbation in the extremal. So, suppose q bar hat is an allowable variation. Suppose q bar hat is an allowable variation where each of the components q hat k is C2 of T0 T1, where my q bar hat of T0 is q0 bar and q bar hat of T1 is q1 bar, right. So, these are my boundary condition, and further I have that the constraint is also satisfied. This constraint is also satisfied for these. So, when I say allowable variations, these are the set of conditions that q bar hat must satisfy. Okay. So, when I say that J is a stationary or q is an extremal of J, stationary at q bar, so then it implies that the necessary condition for this statement is as follows, right. So, the necessary condition for extremal is that J of q bar hat minus J of q bar will be 0 or at most of order epsilon square, right. So, only the higher order terms survive, the lower order terms, the lower order with respect to epsilon terms, they vanish. So, then in that case we are guaranteed, we necessarily get the extremal. Okay. And we saw that let me call this statement as 1. We saw that this is true if this following integral constraints is satisfied. We get that this is also equal to partial q1 of L, where J is integral L dt, right. So, partial q1 of L minus ddx of partial q1 dot of L times the first perturbation in the first component eta 1 plus partial q2 of L minus the derivative ddx of partial q2 dot of L times eta 2 of dt. Okay. So, this is equal to 0. So, having said that q bar is an extremal, this is equivalent to saying that this integral constraint is satisfied. Okay. So, then we need few other assumptions before we move ahead. Since I have that q bar is an extremal and it is fixed. So, q bar is fixed, right, and I am also assuming that the gradient. So, since means that I am assuming, right. So, I am assuming, and also that the gradient of the constraint is non-zero, right, over the interval, over the parameter interval from t0 to t1. We assume, so this means without loss of generality, we can assume that let us say one of the components is non-zero, right. We can assume that del g del q2 is non-zero. We could assume the otherwise, or we could also assume that both components are non-zero, right. So, let me call this assumption as star. Okay. So, since the constraint is satisfied, since I have that g of t comma q bar is 0, the constraint is satisfied, I have that the derivative of g with respect to epsilon, since this constraint is 0, it means that the derivative of this constraint, the constraint at the perturbed value of q must also be 0 at the critical point, which means that the derivative with respect to epsilon of g of t comma q bar hat at the perturbed value set at epsilon equal to 0, that is at the critical point, must also be equal to 0. But this quantity here is nothing but the following. So, this is coming via the chain rule. So, del g del q1 times eta 1. Well, there is absolutely nothing new in this exercise. We have done it in fact more than once to come up to come out with the necessary condition for the extremal. Once in the finite dimensional calculus and in the other time when we were discussing the isoperimetric constraint. So, we are doing a similar exercise for non-holonomic constraint. So, now this is equal to the following. So, del G del Q2 times eta 2. Okay. From here I get that eta 2 is equal to negative del G del Q1 divided by del G del Q2 of eta 1, right. So, let me call this as double star, right. Let me call this as double star. We are going to use this later when we describe the necessary condition. Now, then let me also state another fact. So, recall I have the functional j of y, j of not y but j of q bar equal to integral L dt, right. So, this was my functional. So, here we have assumed that L is smooth. We have assumed that L is smooth. L is smooth function, right. Therefore, which implies that for any smooth extremal q, smooth q bar, I must have that this quantity E2 of L, which is this left hand side of the Euler Lagrange, this quantity Q2 minus partial L, well this is Q2 dot minus partial L partial Q2, this is also equal to, well this is also equal to, well this is also continuous, right. So, this is also continuous function of the parameter t, right, because if L is smooth and it has derivatives up to second order, I must have that this operator acting on L must also produce a smooth function of t, right. So, I can say that now, so further we know that del G del Q2 is also continuous function of t, right. We can further assume that del G del Q2 is a continuous function of t. So, both are continuous functions of t, which means that we can express one continuous function as in the form of the other continuous function, right. Both are continuous functions. So, the ratio of the two continuous function will also be a continuous function, right. So, what I have said is the following: since both of them are continuous functions, so this means that there exists a non-zero continuous function lambda of t such that my E2 one continuous function can be expressed in terms of the other continuous function using this second function. Right now, I have just used a simple continuity argument to arrive at a relation. So, expanding this we see that this is, so or this means that d dx of del L del Q dot minus the partial L partial Q2 is equal to lambda times del G del Q2. Let me call this, let us see what numbering notation we have used. So, we have called this result as 1. So, let me call this result as 2. Okay. So, moving ahead, if we recall 1 now. So, recalling our result 1, we see that the constraint that we have, so recalling 1 and 2 both, right. Well, I do not need 2, but I need this condition. I need double star this condition. Okay. So, recalling 1 and double star, I see that my integral constraint becomes the following. It becomes del L del q1 minus d dt of del del q1 dot of L times eta 1 minus lambda t del g del q2 times eta 2, right. So, all I have done is replace. So, I have used 1 and 2 as well as star. So, this becomes, so eta 2 is nothing but replace. So, now I am going to replace this perturbation eta 2 using my relation double star to arrive at a quantity which is in which I can take out this perturbation eta 1. Okay. So, from here I see that I get the following condition, that I get that this is T0 to T1 del L del Q1 minus d dt of del L del Q1 dot plus lambda of T del G del Q1, right, and then times eta 1, this is equal to, well, dx, this is set equal to 0. So, this is eta 2 is replaced by the relation between eta 2 and eta 1 to come at this particular integral constraint, and again using a version of lemma 2 discussed in lecture 2, I come to the point where I have the Euler-Lagrange equation for L with the holonomic constraint G for the component Q1. I come at the following, that I get del L del Q1 del L del Q1, right. So, del L del Q1 minus d dt of del L del Q1 dot plus lambda del G del Q1, this is equal to 0. Now, notice that from 2 we have an identical equal constraint for the component Q2. Well, if we take the minus on both sides, then the relation becomes identical to this relation that we described 3. So, let me call this 3. So, 2 and 3 are identical, but with component Q2 replaced with Q1. So, I am ready to describe my Euler-Lagrange necessary condition in this situation. So, in compact form, my necessary condition is as follows. I must have that d dt of del q k dot minus del q k of f must be equal to 0 for k equal to 1 comma 2, and my f is equal to f minus, well, we do not have an f here, but we have an L. So, L minus lambda g, where L is the integrand of the functional and g is the holonomic constraint. Okay. So, let me call this result by 4 and also give another reference to all the students where a proper proof based on geometry is provided, geometry. Okay. So, students are asked to also refer this particular reference to look at a more detailed geometry based proof for this situation of functional optimization with holonomic constraints. So, the author is Jacinta and Hildebrand. So, we need to, students are requested to refer to this particular reference, which is a book So, the book's name is Calculus of Variations, Part 1. Part 1, the Lagrangian formulation, Lagrangian formalism, and published by Springer in 96. So, this is a useful reference for geometry based proof of these class of problems that I have just shown. Okay. For the Lagrange multiplier method for with holonomic constraints. Okay. Constraints. Okay. So, I am going to end my discussion on holonomic constraints by summarizing my entire discussion in the form of a theorem and also providing some examples to highlight how this Euler-Lagrange necessary condition is utilized. So, the theorem is as follows. This is now theorem number 12. I see that suppose that I am given q bar is q1 comma q2, q bar is q1 comma q2, which is a smooth extremal, for the functional, smooth extremal for the functional J subject to the holonomic constraint given by g of t comma q bar equal to 0 and the gradient of g of t comma q bar not 0 for t in t0 to t1. So, suppose we have this setup, then there exists a function, a real valued function. There exists a function lambda of t such that q bar, the extremal, satisfies our relation 4, the relation that I have. So, this is the relation I am talking. So, the relation 4, which is the Euler-Lagrange necessary condition. Okay. And then let us look at some examples in this category. So, the example today that I have is as follows. So, I need to extremize j of q bar, which is integral from 0 to pi by 2 of mod q bar dot square plus 1 dt, subject to g of t comma q bar, which is given by this relation mod q bar square minus 1 is equal to 0. So, this is a case of a constraint optimization subject to holonomic constraint. Okay. And further, with my boundary conditions as follows, I have q bar at 0 is 1 comma 0 and q bar at pi by 2 is 0 comma 1. So, this is a problem with two variables. So, again we look at the way to optimize is we directly set up our Euler-Lagrange equation, and so what we have is, so to set up the Euler-Lagrange, notice that my functional for Euler-Lagrange now is L minus lambda t of g, and this becomes square root mod mod q bar dot square plus 1 minus lambda t of q bar square minus 1, right. So, this is my my function for which we need to apply the Euler-Lagrange operator. So, the Euler-Lagrange, the EL equations are, so d dt of q1 dot divided by mod q bar dot square plus 1. So, I am directly applying my Euler-Lagrange equation and writing down the final expression. So, these are my expression when I differentiate with respect to q1, I get the following expression times 2, this is equal to 0, and the second, that is the derivative with respect to q2, I get the following expression q2 dot divided by mod q dot square plus 1 minus 2 lambda of t q2, this is equal to 0. So, I call this expression as A, and we see that I call this expression as A. Okay. So, now we have to solve the system of equation. To solve the system of equation, we see that, so also we all have the constraint. We have the constraint g of t comma q bar, which is mod q bar square minus 1, which is also equal to 0, right. So, we see that my q, my extremal is q is such that the square of its norm will give me, the square of its absolute value will give me 1. So, from here I can assume that q1 and q2 are lying on a unit circle, right. So, the moment we assume that, we directly satisfy the constraint, right. So, we need not worry about the constraint now. So, instead of two variables q1 and q2, now we have just one variable phi to solve for, right, and of course, we have the second variable lambda of t, the second functional variable. So, we have two unknowns phi and lambda, and we have two equations which are given by A. So, we directly substitute these two quantities in A, and we see that, we get the following. Well, of course, if q1 is cos of phi of t, I get that q1 dot is minus sin phi times phi dot, and q2. So, if q2 is sin of phi, then q2 dot is cos of phi times phi dot, right. So, what I get is, from here I see that the absolute value of q bar dot square will give me nothing but phi dot square, right, squaring and adding these two quantities, and then from A, the set of relations from A gives me the following set of equations. So, d dt of, the first relation gives me d dt of phi dot sin phi divided by square root phi dot square plus 1 plus 2 lambda t cos phi of t is equal to 0, and then d dt of phi dot cos of phi divided by phi dot square plus 1 minus 2 lambda t sin of phi of t, this is also equal to 0. So, after plugging in the values of q and q bar and q bar dot is what we get. So, further we take the first derivative, and rather than taking these necessary derivative, notice that if we multiply this first quantity by sin of phi and multiply the second relation by cos of phi, right, and we add these two relations, we are going to get the condition that that sine of phi times d dt of the first quantity phi dot sine phi divided by square root of phi dot square plus 1 plus cos of phi d dt of phi dot cos of phi divided by square root of phi dot square plus 1. This is also equal to 0, right. So, we have eliminated one unknown, eliminated lambda of t by doing that. Now, further we can see that this whole quantity is nothing but the derivative of the following quantity, the derivative of phi dot by phi dot square plus 1, right. So, this whole quantity is nothing but the derivative, and this is set equal to 0 on the right hand side, right. So, students can check. So, this needs to be checked that this is indeed true, right, and which means from here I can directly integrate this relation once to come to the point that phi dot divided by phi dot square plus 1 is equal to a constant, okay, constant. Or in other words, I see that phi dot is also a constant. If this expression is a constant, then phi dot will be another set of constant. Okay. So, the conclusion is that phi dot is equal to C naught, which is a constant, or phi of t, the angle that, or the parameter that, or the substituting function phi of t is C naught t plus C 1. So, it is a linear relation in t. So, now my variable q 1 of t is cos of C naught t plus C 1, and my q 2 of t is sine of C naught t plus C 2, right. So, now we have, all we have to do is to eliminate C naught and C 1, but we have set, so we have two boundary conditions present. So, my boundary conditions are, my q bar of 0 is 1 comma 0, and from here I can immediately see. So, it gives me that q 1 at 0 is 1 and q 2 at 0 is 0. From here I can see that C 1 will come out to be 2 n pi, right. And further I have that the other set of boundary condition, q bar at 1, not 1, but the other value pi by 2, the upper limit of the integral is 0 comma 1. From here I see that C naught comes out to be an integer 4 m plus 1, where m is an integer, right. It could be positive or negative. Okay. Now, also we know that t is from 0 to pi by 2. Why? Because notice these limits here, 0, 0 and pi by 2. So, the limits of t is from 0 to pi by 2. Okay. So, t is from 0 to pi by 2, which tells us that that it is only possible when C 1 is 0 or n is 0 and C naught is 1, right. So, t can remain in the first quadrant only when C 1 is 0 and C naught is 1, right. And in that case my q 1 of t is cos of t and my q 2 of t is sine of t. So, those are my parametric representation of the function, and that completes the discussion, that saying that this function, this extremal lies on the rim of a unit circle. Note, well, We did not even check whether the problem was normal or abnormal, but note that if we were to calculate the gradient of g, the gradient of g is the derivative of g with respect to q1 and the derivative of g with respect to q2, we will see that now since we have evaluated q1 and q2, it comes out to be sin t cos t. Okay, and this is certainly not 0 for all t in the interval 0 to pi by 2 that we are considering. Okay. Okay, so which means that we are working with a normal problem in this case. Okay,